let's prove the chain rule. So the statement of this, as we've seen in a previous video, says that, say that you've got two functions, f and g, and you take their composition and you want to find the derivative. So say that we want to find the derivative at the point x equals to a. So that's like saying f composed with g, take the derivative at the point a. That's going to be equal to derivative of f, plug in g of a, times derivative of the inside function g, and plug in a. And this is going to be valid for any number a such that the derivative of g exists at that point and the derivative of f exists at g of point. Whenever that happens, the composition will be differentiable and its derivative will be equal to that right-hand side. And here we want to prove this equality. And the first thing you might do, the most natural thing you might do, is actually straight up write down the definition of derivative for f composed with g. And you can do that. You end up running into some technical problems. So the proof of this is going to be maybe the most nuanced or most substantive thing we've done so far in the class. So instead of just writing down the definition straight away, I'm going to take a tactic that's similar but also a little bit different. So here's what I'm going to do. So I'm going to start my proof. So I'm going to begin by defining a function. I'm going to call it capital F. And I'm going to use variable u. And I'm going to define this function in two pieces. First, I'm going to say that it's my lowercase f minus f of g of a over u minus g of a. And this is going to be the case whenever u, the input, is anything else except g of a, right? Because if these two things are equal, I can't divide by 0, so it wouldn't make sense to define the function like that. And if u is equal to g of a, I'm going to define this to be f prime of g of a. So why am I doing this? Why is this sort of a natural thing or something that makes sense? This is definitely a difference quotient. And what I'm going to claim to you now is that this function is actually continuous at the point g of a. And so why is that true? If I take the limit as u goes to g of a, then what I'm getting is the limit of this difference quotient. And since I know function f is differentiable at the point g of a, this is the difference quotient for that derivative. So when I take the limit, this is the answer that I get. So the fact that this function little f is differentiable at the point g of a is the same thing, if you like, as saying that this function is continuous at the point u equals to g of a. Okay, so the next thing that I'm going to do is I'm going to take this function and let's introduce variable x, and let's say that x is not equal to a. It can be anything except point a. So for any number x not equal to a, I'm going to take my function f of u, and I'm going to multiply it by u minus g of a divided by x minus a. That's why I had to say that x can't be equal to a, because I don't want to be in a situation where I'm dividing by 0, and I'm going to ask myself, what's this equal to? And if I, kind of plug this in, if u is not equal to g of a, then this function is equal to that difference quotient, and then the u minus g of a is going to cancel on top and bottom, and what I'm going to be left with then is f of u minus f of g of a, all divided by x minus a. So that's valid whenever u is not equal to g of a. What if u is equal to g of a? In that case, this function is no longer that difference quotient. It's equal to f prime of g of a. So that would go there. And when u is equal to g of a, this part would be 0. On the other hand, this right-hand side, when u is equal to g of a, the numerator is going to be 0. So in that special case, both sides are 0. So that means that this equation is true for every single x not equal to a. Doesn't matter what u is equal to. And that's important. So now what I want to do, really, is just take the limit on both sides as x goes to a. And before I do that, I'm just going to sneak in one more step. So this is all valid no matter what u is equal to. So I'm going to make the substitution u equals to g of x. And after making that substitution, here's what I get. So I get capital F of g of x times g of x minus g of a, all divided by x minus a. So I'm just recopying this equation downstairs, but making the substitution u equals g of x. And this is equal to f of g of x minus f of g of a, everything divided by x minus a. And if you're getting a sense of what my motivation is for doing this, I'm basically trying to write down this equation, but without the limits, just by working with the difference quotients. And that's actually a really common trick in higher mathematics. When you want to show that a derivative exists, you start with the difference quotient first and then take the limit. It's exactly what I'm going to do here. I now want to take the limit of both sides of the equation as x goes to a. And so let's look at this term first. When I take the limit as x goes to a, what happens to f of g of x? Well, as x goes to a, certainly u goes to g of a, because g of x goes to g of a. The reason for that is because since I know that g of x was differentiable, I assumed that it has to also be continuous. Definition of continuity is telling you that if x goes to a, then g of x goes to g of a. What happens when g of x goes to g of a and I take the limit? Well, this function is continuous, so I can take the limit just by plugging in g of a. So what do I get when I plug in g of a? Nothing but f prime of g of a. So this term right here becomes lowercase f prime, plug in g of a. As I take the limit, x goes to a. Now when I take the limit of x goes to a of this is the difference quotient for the derivative of g at the point a. So when I take the limit as x goes to a, that's the very definition of g prime of a. And look at that, I've already got the right-hand side there of the chain rule. It's kind of nice. And now what happens when I take the limit here of as x goes to a? Well, this is the difference quotient for the composition, f composed with g, right? This is f composed with g, plug in x, minus f composed with g, plug in a, divided by x minus a. So when I take the limit of this side as x goes to a, that's the very definition of the derivative of f composed with g at the point A. So that's a clean formal proof of the chain rule with nothing skipped, nothing hidden behind the curtain.